Good evening. We're talking about projectiles, projectile motion, as an example of motion in two dimensions. That's motion on a plane as opposed to on a line. Other examples of motion in two dimensions will be circular motion, orbital motion, which could be any of the conic sections, and perhaps relative motion. But this is just projectiles, very commonly studied at early college level or advanced high school level. Now the last time when we looked at the, oh by the way, we're assuming no air resistance, a locally flat Earth, and g equals 9.8 meters per second squared is the acceleration due to gravity on the surface of the Earth. Now we have the kinematics equations, which we started off and I didn't really get involved with too much. Let's look at how high should something go. Actually, maybe we should derive this one. Now, I just square this definition. This comes from the definition of acceleration. Now, if I just take a common factor of 2a, out of this one here, I can get 2a ut, there it is there, 2a squared t squared times a half, which is u squared plus 2as. Now that's how we derive the third kinematics equation. This one is number 3, this one is number 2, and this number is number 1. So let's ask a question with regard to this one. How high will a stone go if thrown up at an initial speed, which we'll call a launch speed, of 10 meters per second? So here are our givens. U is the initial speed is 10 meters per second. Remember I said list your givens, identify the unknown. V is the final speed. At the top of the trajectory, the thing goes up, stops, and comes back down again. And the acceleration due to gravity is negative 9.8 meters per second squared because it's pulling back to Earth. Now we identify the unknown, and we identify the unknown to be the height. This is an indirect given. So we now solve. So we go 10 meters per second squared minus 2gh. And we need to find h. Two times 9.8 is 19.6. And we found that it's approximately 5 meters. Okay? So that's just an idea of how this one works. Now this is very important for projectiles because this would be the time of flight for our projectile if it was thrown up and had to come back down again. Okay? So we're still on projectiles. Let me clean that now and let you get your heads around that. Yeah? Now we're always dealing with the flat earth and no air resistance. Here are some of our projectiles. The projectile that we did that went up and came down. But I could give it a sort of a horizontal speed, or even a greater horizontal speed, but it still goes up to the same height if the vertical component of motion is 10 meters per second. Okay? So all these will have the same time. Same time of flight, which is T max. If the vertical component is 10 meters per second, well, we could go and find different things. The range is going to be whatever horizontal speed it has times the time of flight. In this case here, VEG. Okay, I forgot to tell you something. What is the time of flight? Well, 2 times 5 is 10. For this particular place here, the time of flight is 1 second, because t is 2h over g. Remember that. We did this already. Maybe I'm moving too fast. Doesn't matter, as I do problems, you'll see things take up shape. Now, from the kinematics equations, we can just write down the the equations of motion for projectiles. Now, for the position, in the y direction, we might start off not necessarily at y equals 0. We might start off at y equals h. So that could be a h. We start off somewhere, and we use this equation. So we can put in for y0, this one over here. In its unit vector in the j direction. Now for Rx, x is just Vt. Now what are the V's, the Vx's and the Vy's? Well, the Vx's and the Vy's works like this. That's V0, this is V0 cos theta. and this is v0 sine theta, the components of speed in the x and the y directions. So we put input those. And there we have the position, or the position vector of a projectile as a vector in both the x and the y direction. In other words, its exact position. Now the speed of the projectile is dr over dt. dr by dt for this one. Wait now, what did I do wrong here? There's a t in here. Okay, so take the derivative of this guy here and I get v0 cos theta in the I direction plus, for this one here, v0 sine theta in the j direction. And the acceleration is the derivative of this guy. Derivative of this guy with respect to time is 0 in the I direction. The derivative of this time with respect to time is just negative g j. And that's the way it should be. There is only one acceleration, the acceleration due to gravity, which is vertical. Okay? Now that's really all projectiles. We could look at other things though. We could do this, right? All right. From this one here, we can find the time of flight. Actually, I'm going to leave that to part 2. And I'm going to stop it here because that's enough for this little lesson. Okay, so I want to put all these things together because there's a lot of detail in here. And just, you know, be patient. I'll do a problem and I might make a couple of mistakes in the problem. You guys can email me in. Projectiles are very easy. It just looks like a lot of figures and a lot of calculations. And every man and his dog has a way of looking at them. You guys, when you work through these things, you'll find your own perspective, all right? You can also solve projectiles by looking at the vertical motion and the horizontal motion completely independently. You only need, the main ingredient for a projectile motion is the time the thing is in the air. The other main ingredient is the horizontal speed. The horizontal speed times the time in the air gives you the range. And you can start off on a height and end up in a trench, or you can stay on a flat ground, or you can fall straight down, or you can just roll over a cliff. They're the various different things, and we look at them in more detail. Now I'm going to stop.